So with that mathematical toolbox of phasors, let us try to analyze what happens to our telegraphs equations when I now allow for excitations to be purely sinusoidal at a single frequency, right? So let us recall our telegraphs equations. We had dou v by dou x as minus L dou I by dou t and dou I by dou x. Okay, so these were our telegraphs equations. You can sort of think of solving these in the frequency domain as also a way of trying to sort of remove the time variable, right? We will see very shortly that that's the intent, right? And that we'll only look at the spatial variation, right? Remember that I told you that incorporation of speed of light delay on transmission line now makes voltages and currents as functions of both x and t. Now we are somewhat trying to go into frequency domain and restricting our view of how these voltages and currents change for only a single frequency excitation. It is perhaps a way in which we are trying to eliminate one of the independent variables, because we are saying that in time it's only going to be a sinusoidal waveform, right? And we are only interested in perhaps the amplitude of these oscillations and how this amplitude changes over various locations or positions on the transmission line. So we want to keep the variability in x and somehow discard the variability in t by saying that it is going to be always a sinusoidally changing time dependence, right? And no other time dependencies are expected. So in such a scenario where I can write V as V tilde e to the j omega t, right? And I can be written as I tilde e to the j omega t, right? I can substitute these into the telegraphs equation and see how the equations simplify, right? So let us say take equation 1. So I have dou v, which is v tilde e to the j omega t. Remember, v tilde can be allowed to vary with x, right? It's only the time dependent portion of the voltage which has been represented as e to the j omega t, right? So in fact, we can even keep this more clear by saying that it is only the real part, right? We are not dealing with any complex numbers necessarily for voltage or currents, right? So we are just saying that we are representing the cosine as the real part of e to the j omega t, and the reason to use exponentials is because that when we do derivatives or integrals on these functions, we simply get back the same e to the j omega t only multiplied by a prefactor, right? So the real part, I think I can sort of take it out, right? These are the advantages of using mathematics, right? So you can sort of rearrange these linear operators, right? Similarly, I can say real of okay. So remember that v tilde and I tilde are only functions of x. Right? So you may also ask, sir, how is it that this is something that we can be absolutely sure of, right? So it was all well and good when we had, say, constants a and b, right? When I talked about, say, sinusoidal excitations to a linear system, right? Remember that in the time domain analysis, we said that solving the wave equations, that the appearance of t and x have to be together, right? And now I am actually having the separation, right? So I'm actually writing the solutions for v and I as actually product of two functions, right? One purely as a function of x and one purely as a function of time, which is represented by the e to the j omega t, right? A very specific form for time dependence. You may wonder or ask me, sir, is this right to do this, right? Because you told us that wave equations or these equations will only have solutions for v and I that are that should have t and x come in a very unique way, right? Which is t plus x square root of LC or t minus x square root of LC. How is it that you are now separating a time dependent function in a space dependent function, right? It's a absolutely good question that you should ask yourself. And this is again exploiting another mathematical theorem which says that if I have linear and homogeneous differential equations, then I can have my solution which will have an outcome where I can have separation of these variables, right? So it assures us, right, when I have equations like this, which is both linear and homogeneous, then I can expect to have a solution to the functions v and I that are separable in the two independent variables, right? So there is another mathematical theorem that is allowing us to write solutions in this form, right? By the way, linearity, I can give you a very quick hint as to say that these are linear equations. For one, we don't see any quadratic terms, right? Neither do we see v squared, sorry, we don't see any higher powers of v squared, v cube, so on, or I squared, I cube. We don't see those, right? Nor don't we see dou v by dou x or dou v by dou t squared, right? So I don't see any higher powers, right, greater than 1 for either the variables themselves or its derivatives with x or t, right? So since I don't see these terms in the equation, I can say it is a linear equation. If I only have v's and i's or first derivatives or in x and first derivatives of t, right, I can have second derivatives too, no problem, right? But I should not have any term that is raised to a power, right? That is when I can say that a particular equation is linear, right? And the second is, I said, homogeneity, right? So these are homogeneous equations. And another trick to say that a particular equation is homogeneous or not is if I remove all the derivatives and all the variables to one side of the equation. On the right hand side, if I only have 0, right, that is no constant scalars, right, that are not dependent on any of the independent variables or the dependent variables, right. So if I have such a situation, then I can say that it is homogeneous, right? So for example, dv by dx is equal to 4 is not a homogeneous equation, right? Whereas the same equation when equated to 0 is a homogeneous equation, right? So I should not have constant scalars, right, within the equation. Then I can say it is homogeneous, right? So when linearity and homogeneity is um, satisfied, then I can say that the solution to V can be written as some function of x and some function of time. Right? I can actually separate the independent variables x and t into independent functions. Right? Now, if you're still wondering that even after separating these, can I still get the t plus x square root of LC or t minus x square root of LC? You can probably see that the solutions probably ought to be of the form that have the same form of time domain, right? So even before we go into solving this, we are able to make so many conclusions from well-known mathematical principles, right? So we can say that if G was of the form e to the j omega t, then f will also be some e to the j some function f of x, right? In fact, it will be a linear function of x, right? So maybe I can even write kx, anticipating what is to come. So now if I were to multiply these two, you can notice that f times g gives us e to the j kx plus omega t. Now you can see that the t and x can combine itself, right, in the way we want, right? So keep this in mind, right? So there is many mathematical principles that allow us to sort of make certain conclusions very comfortably. See, even though we don't know much about the details of any of the circuits, right, we are able to make a lot of predictions, right, on how the functional forms of these are going to look like, right? So here e to the j omega t on the left hand side is not a function of x, right? It's only a pure function of time. So I can remove that outside the derivative. So I just have real part of e to the j omega t dou v tilde by dou x is equal to real part of minus L. So remember, I tilde is not a function of t, it's only a function of x, right? So I can pull that out, and the time derivative acts only on the e to the j omega t, which brings down j omega and e to the j omega t. Okay. So the convenient part of this is I can essentially just cancel out, right, the e to the j omega t's from both sides, and now I have only a equation that is only a function of x, right? So the time dependence has been completely removed. Right? So we are saying that if the complex number inside the real part of the argument is the same, then we essentially say that now v and I are complex numbers, right, that are only allowed to be functions of x, right? So we have a new differential equation, right? Maybe we can call this as 1 prime, right, where we've basically looked at how we have transformed an original partial differential equation which was both allowed to vary as a function of x and time, and now we have only phasors that are dependent on x alone. The time dependence has been completely removed, right? Because we know that ultimately when we want to know the actual voltage or current, we are simply going to take these phasors and then use these relations, right? So, we solve for the phasors, we multiply it by e to the j omega t and take the real part of it to get the real voltages and currents that we would measure if we were to go into the lab and take a multimeter or a current meter to start measuring the voltages and currents, right? Similarly, you can also show that the second telegraph's equation transforms into right. So, this is a very simple first order differential equation which you can probably readily look to solving it, right. Nevertheless, still V and I are coupled to each other, right. So, this coupling comes from the inherent coupling between electric and magnetic fields, right. So, let us quickly look at what happens when I try to solve these two simultaneously. We should be led to the same kind of equation that like the wave equation, but now the time dependence is very predictable, right. So, in fact, we could have come to the equation that we are going to see also by taking the wave equation directly and implementing the phasors into the wave equation directly, right. So, when you take a second derivative in time, you will basically remove one more j omega from the exponent, right, and you will have a minus omega squared, right. So, you can also verify whether you come from the telegraph's equations or from the wave equations, you will essentially see the same result, right. So, I am going to take the second derivative, right. So, take 1 prime, equation 1 prime, and differentiate it with respect to x, right. So that I get right, and this dou I tilde by dou x I can substitute from the second telegraph's equation, and I should simply get minus j omega L minus j omega c times b. Okay, so dou square b by dou x squared is, so j squared is minus 1, so I get minus omega squared LC b tilde. Okay, so we have a second order equation, but we only have one variable v tilde instead of both v tilde and I tilde. We have basically eliminated I tilde from the two equations, and we end up with a second order differential equation, which should remind you of a harmonic oscillator, right. So, you've probably done this in your grade 12, where you had the second derivative of a function being proportional to the function itself, right. So, in this case, the second derivative of voltage, right, is essentially proportional to the voltage itself, right. So, doing this math rigorously and sort of going through step by step is only a way to give you some comfort that you can deal with these phasors just like you dealt with the original variables v and I, right. So, it is just that we have conveniently separated out the x dependent part, right, from the time dependent part, right. The time dependent has been explicitly forced to behave as e to the j omega t, because we know that linear systems will not create any new frequencies, right, and in that case we notice that we have a way of just looking at the spatial dependence, right. So we'll basically take this equation up as the beginner to start to look into more details, right, of what happens when I have different kinds of loads. Remember that we stepped into the study of transmission lines using frequency domains for even complex loads, right. We said that frequency domain allows us to be able to handle all kinds of loads, right, complex loads. It's a little less intuitive, but it will allow us to look at more comprehensive loads, right. By forcing us to look at just one particular frequency, we are able to make so much simplification, right. So this power, right, of analyzing the circuits at single frequency is something that truly can be appreciated when we go to the case of the generalized distributed model for the transmission lines, right. So remember that the original distributed model we came up for the transmission lines also had resistors, right, to indicate losses, and we actually simplified by assuming these resistors were 0 by saying that in the time domain analysis we can keep things a bit simple, right, by just looking at the L and C and just looking at the time delay effect. Now I can say confidently that even this distributed model can actually be analyzed in its entirety using the phasor description and looking at it in the frequency domain, so that we are looking at only one frequency, right. So this uh, power of analyzing these circuits at a single frequency can truly be appreciated when we start looking at the distributed model, right. If I were to try to choose to solve this purely in the time domain, right, it would have been fairly cumbersome, right. I would say it would be very mathematically tedious, right. But we are going to see that this is going to uh, become quite simple and manageable equations, in fact of a very similar form as we saw for the lossless line, right. So in this case we can say that this R and L, right, we have two elements, that is between the input and output ports in series, right. Perhaps go back even a step further back, right. We can always go back to saying that del V, right, which is the potential difference, should be I times the impedance, which is R delta x plus j omega L delta x. Right. This already assumes that we are using a sinusoidal excitation. So I can say that these are tildes, right. So how did we get this equation? If we wanted to get to the grassroots, we can say that delta V, which is both a function of x and time, right, is essentially I times r delta x plus L delta x times dou I by dou t, right. Now if I were to assume that V was V tilde e to the j omega t, I is I tilde e to the j omega t, then dou I by dou t is j omega I tilde e to the j omega t, right, and you can say that r delta x can be removed. I is I tilde e to the j omega t. Dou I by dou t is also proportional to I tilde e to the j omega t with a proportionality constant of j omega. So I can right, and delta V is essentially right. So the e to the j omega t, the time dependence goes away, and we are essentially left with right, and I can move the delta x to the left, and you essentially get dou V tilde by dou x for small delta x. So I made a mistake here. There will be a minus sign, because remember that as I go from V to V plus delta V, the potential goes down, right? Assuming that current is flowing from left to right, it should go from high potential to low potential, right? So I can say there's a minus sign throughout this. Okay. Similarly, we can say that the change in current, right? So some current is going to flow through. So there's a reason that we use conductance, right? Because conductance is had in parallel, right? So we'll make use of the fact that these two elements are in parallel, right? And they are inverse of the impedance will add, right? Or the admittance. So we'll use that to our favor to estimate the net impedance, and essentially whatever delta I have going out, right, is essentially the sum of the currents from these two branches, right. So this is your Kirchhoff's current law, right. So we have minus of delta I is equal to C dou V by dou T, right, plus G times V, right. So this is just writing Ohm's law, right. So V by R is I, right, So 1 by R can be written as G. Right. So 1 over the resistance is the conductance G. Right. So if I sum the branch currents through the capacitor and the resistor, right, that has to be essentially negative of delta I, right, the current change between the input and the output. So we can again go for taking the notation, the phasor notation for currents and voltages. C times, oh, I forgot the delta x, right? So okay, never forget the delta x. C times, so dou v by dou t is essentially v tilde j omega e to the j omega t plus g times v tilde e to the j omega t. Right, on the left hand side we can probably write it out as delta of I tilde e to the j omega t. Right, so we should essentially get minus dou I by dou x is g plus j omega c times v tilde, because the e to the j omega t conveniently gets dropped out, right. So you can see that these two equations combined, right, can now be called the generalized telegraphs equations, right, when solved for in the frequency domain for a very specific frequency of excitation. We actually have very simple, right, equations, very similar looking like the ones we had for the lossless case, except for the fact that there is now an R and a G, right, that is adding on to the j omega L and j omega C. The equations and their appearances look very similar, right. So because the frequency domain allows us to simplify even the distributed model, we'll actually start by looking at the distributed model, and we can always go back to the lossless case by setting R and G to be 0, right. So that way we can develop something more generalized and we can actually make use of it even for the case of the lossless transmission line, right. All right. So from the next week onwards, we will continue from this point, right, and we will start making certain observations in terms of the spatial dependence, right, for voltage and current, and what this means, right, and if there are some interesting behaviors that was not brought out when we were looking at the transient analysis in the time domain, if we are able to make some interesting observations in the frequency domain.